Welcome to the content material for Class 19 of Engineering Statics. You should be watching this video before your 19th class. In this lesson, we will learn what kinds of internal forces exist in two-dimensional members and how to solve the internal forces at a particular point of a member. When a beam has forces applied to it, there are reaction forces inside the beam at every point. There are forces perpendicular to the beam's cross-section, which we call the normal force. There are forces tangent to the cross-section, which we call the shear force. And there are bending moments. Together, we can call these three forces the internal loadings. These internal loading forces are important to designing a structural component. For example, a material like concrete will have a shear strength. In other words, if the shear force is greater than the shear strength of the material, the beam will fail. So, how do we determine the internal forces of a beam? Well, we can use the method of sections. We can take this beam and draw an imaginary cut line that breaks the beam into two pieces. At the cut point, we can assign normal, shear, and bending moment forces to represent the internal forces. We assign the internal forces for the two different sections to be equal and opposite. Then we can use equilibrium equations to solve for the internal forces. Before we do that though, let's establish sign conventions. In other words, what do we call positive or negative forces? For normal forces, positive is defined as a force that creates tension. For shear forces, positive is defined as a force that acts to rotate the member in a clockwise direction. For bending moment forces, positive is defined as one that bends the member in a concave up manner. So here is the general procedure for analyzing the internal forces at a particular point in a beam, such as this point. First, determine the support reactions. Second, draw a section line through the point where you want to know the internal forces. Third, choose one of the segments to draw a new free body diagram. Choose the segment with the least number of external forces applied. Indicate the internal forces at the section line. And fourth, set up and solve equilibrium equations, usually starting with the moment. Let's look at some examples at how to do that. So in this example, we're going to find the internal forces at two different points. One just to the left and one just to the right of a 6 kilonewton force. And we'll call those points B and C. So as usual, the first step is to find the reaction forces. I'll start by taking the moment about the point D. Doing this allows me to solve for the force A, and I find that A is equal to 5 kilonewtons. Next, we can sum for the forces in the y direction. We can solve for dy. dy is equal to 1 kilonewton. And by considering the forces in the x direction, we see that dx is equal to 0. Now that we have our reaction forces, we can start by cutting sections. So if we want to know the internal forces at point B, which is just to the left of the 6 kilonewton force, then we'll start by drawing a section that starts at the left hand at point A. So at point A, we have force A, which is equal to 5 kilonewtons. That's the only external force applied. So here we'll draw the internal forces. We'll draw the normal force, and we'll call that NB. We'll draw the shear force, call that VB, and we'll draw the moment force, and we'll call that MB. Now we'll use our equilibrium equations to solve. Summing the forces in the x direction, we see that NB is equal to 0. Summing the forces in the y direction, we find that VB is equal to A, which is equal to 5 kilonewtons. Finally, we can sum the moments about the point B. We find that the moment about the point B is 5 kilonewton meters. So putting this all together, we find that the normal force at point B is 0. The shear force we'll consider positive because it will rotate the section in a clockwise direction. So it's a positive shear of 5 kilonewtons. And the moment about the point B would tend to curl the beam upwards, concave upwards. So that means that it has a positive 15 kilonewton meter bending moment. And next we move on and we'll do the same thing now for the point C, which is just to the right. So this time we'll use the right hand section, including point D. Don't forget to include this moment that's applied here, which is a 9 kilonewton meter moment that's applied at point D. And we'll do the same thing. So we have the normal force at C. We have the shear at point C. And we have the moment about point C. So we can solve. Same thing, sum of the forces in X. We see that the normal force is 0. Sum of the forces in Y shows that the shear force is equal to dy, which is equal to 1 kilonewton. And summing the moment about the point C, find that the moment about point C is 15 kilonewton meters. So again, we'll put our answer here. Find that the normal force at point C is equal to 0. The shear force is negative 1 kilonewton. It's negative because it tends to rotate in the counterclockwise direction. So we call that a negative shear. And the moment at the point C is positive because it tends to curl or bend the member concave upwards. So 15 kilonewton meters. In this example, we're asked to find the internal forces at point C, which is in the middle of this beam. So we start, as always, by solving for the reaction forces. Draw a free body diagram. Start with the forces in the x direction. We see that AX equals 0. Sum of the moment about the point A. So B causes a positive moment. Two external forces are negative. And solving for B, find that B is 13.75 kilonewtons. And we can take that information and do the sum of the forces in the y direction. Solve for AY. Find that AY is 11.25 kilonewtons. Now that we have our reactions, we're going to create a section. So we're going to cut our beam in half. We're going to cut it at the point C, and we're going to choose one side. I'll choose the right-hand side because that has slightly less forces applied to it. So we have the force B, which is equal to 13.75 kilonewtons, and we have this external force of 15 kilonewtons. And we're going to draw our forces. So we have the normal force, we have the shear force, and we have the bending moment. I'll start by showing that in the x direction, the normal force is equal to 0. And then I will take the sum of the moments about the point C. So B causes a positive moment. And we can use this to solve for the moment C. Find that the bending moment at point C is 18.75 kilonewton meters. And finally, we can take the sum of the forces in the y direction. So the shear moment is upwards as we drew it. So we find that the shear force at point C, as we drew it, is 1.5 kilonewtons. So let's go back and look at our picture and figure out the signs. We see that the shear tends to rotate clockwise, so that will be positive. We see that this moment tends to bend it in the concave upward, so the bending moment is positive. So our final answer will be that the normal force is equal to 0. The shear is a positive shear at 1.25 kilonewtons, and the bending moment is a positive bending moment with a magnitude of 18.75 kilonewton meters.